See if we can find an expression for the current, but now when the charges are moving at some angle with respect to the area. So initially in the last part, the charges were moving perpendicular. So the angle between the charges and the perpendicular direction was 0. But now, what if there's some angle with respect to the perpendicular direction? In this case, what would the current be? So this situation is the situation before the charges go through the area. This is what happens when the charges go after the charges go through the area. They occupy a volume. And so we're going to use the same kind of analysis that we did before to find out an expression for the current that goes through the area. So the distance, the charges that have moved, what is the distance L of this volume that the charges have moved during a time delta t? Distance is the speed times the time. Okay, now if you make a vector A that's perpendicular to the area, it might be difficult to imagine this in this three-dimensional representation, but imagine if you're looking from this side, looking this way, then you can see basically the side only, and the area in this case is this, and it's coming out of the page. So the area vector, this area vector is perpendicular to the area, and the charges now are moving with some angle, with a velocity v, which is at some angle with respect to the area. In the previous case, previous file we took, the velocity was in the same direction as the area, but now there's some angle with respect to the area. So if you'd want to try to imagine how it looks like, you can always imagine this side view. This is an attempt to make a three-dimensional view of what's happening. So what is the volume of this shape? It's not a right-angled volume like the other one. So what is the volume? This is a purely geometrical issue. So we're not going to go through the geometry of it. You can try to prove this on your own, but you can show that the volume of this shape is the area times the length L, like before, but then you multiply by cosine theta, cosine of this angle theta, where theta is the angle between what? It's the area vector is perpendicular to the area, and the velocity is at some angle in the same direction as the side of this volume. So this is what the volume is in the new case, for the case where the charges are going at some angle. So you can always write L as V delta t, and then the volume will be A V delta t cosine theta. It's exactly the same as before, but we've added a term, we've multiplied by cosine theta. So we'll ask the same question we did before. During a time delta t, how much total charge delta q has passed through this area in the time delta t? And we want to write it in terms of something called small n, which is the number of charges per unit volume. What must you multiply small n by in order to get the total amount of charge that goes through the area? The same answer as before exactly. If you multiply small n times the volume, you get the total number of charges. But then we didn't ask about the total number of charges. We asked about the total charge. So you have to multiply by the charge of each one of the charges. But now the volume is different than the previous case. The volume is AV delta t cosine theta. And so this cosine is what will make the difference to the case before. In the previous case, the angle was 0. The charges were moving perpendicular to the surface, so they were moving at an angle 0 with respect to the area vector. And so cosine 0 is 1, and so that's why this term didn't appear before. But now, because of the angle, you get this cosine term. So we're going to do the same thing as before. We're going to define n times q times v. We're going to call this j. We can rewrite this as ja delta t cosine theta. And then the average current is the same as before. It's the same definition. It's delta q by delta t. When you divide delta q by delta t, what will be remaining on the right-hand side? You get ja cosine theta. So the difference between this case and the case where the charges were moving at 0 angle is that you have this cosine theta term multiplied by. Now, whenever you see something that has something times cosine, you can immediately start to guess that we're going to use a dot product here. But the problem is that j so far, it's a scalar. We defined it as a scalar. It's just numbers multiplied by each other. The area can be known as a vector. We've taken in Gauss's law that area is a vector. You know what area means as a vector. So why don't we elevate j from being a scalar quantity to being a vector? So let's define J to be NQV, but V vector, not V now scale magnitude. So now J has a vector nature to it, and you can rewrite the average current as J dotted into the area. So get the J vector, get the area vector, and take the dot product, and that will give you the average current through the surface. Just looking at this J vector in a bit more detail, N is the number of charges per unit volume. It's a positive number always. But Q, the charge of each one of the charges could be positive or negative. You could have positive charges like a proton or negative charges like an electron. So the charge can be positive or negative. And then the velocity is just the velocity of each charge. What happens when you have positive charges moving with a certain velocity? What's the relationship between the velocity vector and the J vector? Well, because small n is positive, and because the charge in this case is positive, then J and V have the same direction. What happens if the charges were negative and they're moving with the same velocity as before? The number of charges per unit volume is positive, but now Q, I can write it as minus magnitude of Q. So this minus sign, I can put it with the minus V, with the V, so you get minus V. So the J now moves or points opposite the velocity vector when you have negative charges. And this is going to be very important in defining positive and negative current, as we'll see later.